This is ACT Math Additional Concepts, Counting and Grouping. Counting and grouping questions are those questions on which you are asked to figure out how many different ways you can take a number of people or items and group them together or order them. Counting and grouping questions do include combinations and permutations questions. Some students are familiar with those terms. These questions, like a lot of the more advanced additional math concepts that show up on the ACT, vectors, matrices, logic questions, counting and grouping questions are generally pretty darn simple if you know the information in this section. These questions should not pose a big issue to students that are familiar with this material. We're going to start off with what is known as the fundamental counting principle. Pretty much all of the strategies and techniques that we will talk about in this section, indeed all counting and grouping, pretty much goes back to this fundamental counting principle, which is why it is called the fundamental counting principle, because it is at the base of everything that we will do from here on out. I'm going to read the fundamental counting principle here and highlight some stuff. But just know that as I read through the fundamental counting principle, it's not going to become completely clear what the heck this fundamental counting principle is until we actually start doing some examples, and that's fine. So if there are A, possible options or outcome for one event, B, possible options or outcomes for another event, C, possible options or outcomes for a third event, if we want to find the total possible options or outcomes when we combine these events, what we do is we simply multiply together. We find the product of A, B, C, and so on. So as a very quick, simple example, let's say there are 3 letters that we have to choose from to make, I don't know, some sort of a code. And let's say there are 4 numbers, 1, 2, 3, 4. You know, if we just start thinking about how we might list these out, we'd have A1, A2, A3, A4, and then of course we would have B1, B2, B3, B4. I'm not going to write them all out, but we would have 4 Bs. We would have 4 Cs, right? So there's 4 As, 4 Bs, 4 Cs, which means there's a total of 12. However, we could arrive at that 12 simply by multiplying the number of options for our letter by the number of options for our numbers. There are 3 possible ways that we could pick a letter. There are 4 possible ways that we could pick a number. Therefore, there are 3 times 4, which equals 12, total ways that we could group one letter with one number. And by the way, if we were to add another category to this, let's say we were to add a punctuation mark. Let's say there were a exclamation point and a question mark. So we could do one letter, 1 digit, and 1 punctuation mark. Then all we would do, instead of just 3 times 4s, we would do 3 times 4 times 2. Again, 3 possible letters, there's the 3, 4 possible digits, there's the 4, and 2 possible punctuation marks, there's the 2, and this time we would get 24. That's what the fundamental counting principle says. It says if there are A ways to do one thing and B ways to do another and maybe even C ways to do a third thing, if you want to find out how many ways you can combine or form groups out of those 3 things, you just multiply all the numbers that you're given. Again, rather simple concept. So in example 1, I suggest that you actually just watch me work through this, although it is going to be very easy for some of you. I'll give you an opportunity on later examples to go ahead and work through on your own. But right now, here's what I'm going to do. I'm going to read through this. On her summer reading list, Eugenie must choose from 8 different novels and 5 different biographies. If she must select 1 book of each type, how many different novel biography selections are possible? So I'm going to go ahead and circle. I didn't mean to do that. How many novel biography? So again, you can see this is what I was talking about when I said, when I described what counting and grouping questions look like. You can see that we're being asked how many different ways, how many selections are possible. So we're grouping 1 novel with 1 biography, and we have to find out how many different ways we can do that. Again, very simple. So what I'm going to do here, I'm going to give you a little preview of the box method that we're going to learn in another page or two. I'm going to draw 2 boxes. those two boxes represent my two choice fields, the two things that I have to select. I have to select one novel and I have to select one biography. So I'm going to draw those boxes and I'm going to label the first box novel, the second box biography. Then what I'm going to do is in each box, I'm going to fill in the number of options, the number of possible novels, and then the number of possible biographies I can choose from. And of course, from the question, I've got 8 possible novels, I've got 5 possible biographies, and the fundamental counting principle says that if I want to combine one novel with one biography, and I have 8 ways to choose a novel and 5 ways to choose a biography, then I have 8 times 5, which is 40 ways to make these novel biography selections. So the answer here is 40. Now, in example 1, we should note that we were given a separate and distinct number of options for the novel choice field and for the biography choice field, but that won't always happen. In other cases, what's going to happen is you'll be given a single pool of items from which you need to select all of your choice fields, or from which you have to make all of your selections. If you want to try example 2 on your own, which is an example of the type of question I was just referring to, you can. If you want to watch me work through it, that's fine also. A certain ice cream parlor offers 6 different toppings for sundaes. How many pairings of 2 different toppings from those offered are possible? So how many pairings, 2 different toppings are possible? So again, what we're going to do here is we're going to start off with that box method I was just talking about. I'm going to draw 2 boxes. Why am I drawing 2 boxes? Because I've got 2 toppings, topping 1, topping 2, that I need to select. Of course, for my first topping, I have 6 options, so I'm going to write that 6 in the topping 1 box. But here's the significance or the implication of a single pool type question is that once I make my selection for my first topping, so let's say the first topping I choose, what's a good ice cream topping, Jimmy's or Sprinkles or whatever you guys want to call them. So once I make that selection for that first topping, I no longer have, because the question does say I have to have different toppings, I no longer have that one that I have selected in the first position available for the second position, which means I now need to decrease the number of toppings I have as options for the second topping. So I go from having 6 for the first topping, I make that selection, I have to take whatever topping I chose out of my pool, and now I only have 5 options left for the second topping. Then, of course, fundamental counting principle says I multiply those 2 numbers and I get 30. So there are 30 possible pairings of 2 different toppings at this ice cream parlor. For example 3, another variation on example 2, just slightly more complex. I might go ahead and try to take a stab at example 3 on your own, especially if you're feeling fairly confident by this point. If you are going to do example 3 on your own, do it with the box method, label the boxes, fill in your options, and go to it. To access their class website, students must choose a pin consisting of 1 letter followed by 2 digits followed by another letter. The letters may repeat, but the digits may not repeat. How many such pins are possible? I'm just going to go ahead and circle that whole thing. How many such pins are possible? Okay, so what do we got here? We got 1 letter, then 2 digits, and then another letter. So there's 4 choice fields. The 4 choice fields are the first letter. These are the digits. I'll just write digs. And then this is letter 2. Okay, so letter 1, letter 2. So 4 choice fields, the 2 letters, and then the 2 digits in the middle. There are 26 letters in the alphabet. I do have students ask me that question. I will tell you that on the ACT, often the question will just come out and say that there are 26 letters, but you should know that there are 26 letters in the English alphabet. So we have 26 letters. Then there are 10 digits. It's very important that you remember that the digits are the integers from 0 to 9, and there are 10 of them. You will see quite a few counting and grouping questions that do involve digits or codes that contain digits, and you do need to know that there are 10 digits. Now, here's a very important point. The digits may not repeat. So as soon as we choose the first of our 2 digits, we have to remove from the number of options whatever digit we chose for the first digit, which means we only have 9 options left for that second digit place. And then finally we have letter 2, which is also 26, because remember, the letters may repeat, and therefore it doesn't matter what letter we choose for this first position, we will still have all of our letters available to us for that second position. Now, I know that if you did do this on your own, you probably multiplied these all out and got some gigantic number, and that's fine. I will tell you, however, that on the test, it is very likely, actually more likely, that the answer would look something like this or something like this. In other words, ACT is not really concerned whether you can punch this calculation into your calculator and get some gigantic number as a result. They're really more concerned with whether you can actually lay out the calculation, whether you actually know how to set up the calculation based on the fundamental counting principle. Moving along, top of the next page, we've got to talk about combinations and permutations, which are just a specific kind of counting and grouping question. Again, some juniors, definitely some seniors, have already heard about combinations and permutations. I have found, however, that students' knowledge of them and nimbleness with them is definitely needs some work. So we are going to go through our discussion here of combinations and permutations. If you already know this stuff, obviously you can watch the video at a higher speed, but let's get to it. So in terms of examples 4A and 5A, what I would do right now is I would actually pause the video, I would read these two examples, and I would just think for a moment about what the difference is between the two. So go ahead and do that. So in example 4A, which obviously we come right out and say this is a combinations question, this is a permutations question, but if you've already read these, you can see that there actually are some very clear similarities. You've got in each question you've got a 3-member student council, you've got 5 candidates running for this student council, 5 candidates running for this student council, and then both questions are asking pretty much the same thing: how many different student councils, So there's a lot of overlap here, but the fundamental difference between these two questions is that in the case of example 5A, the permutations question, we've got positions. We've got one person serving as president, one as vice president, one as secretary. And that is a very significant difference on counting and grouping questions, and it has big implications for how we will make our calculations and how many possible groupings there will be. Down in the a little bit further here in the middle of the page, we talk about the difference between a combinations question and a permutations question. In a combinations question, I'm going to go ahead and highlight some stuff here. Order does not matter. We can move the items around. We can move the items in any particular group around to a new place, and we do not produce a different group. So if I have Al, Beth, and Casey, okay, so one guy, one girl, and one name that could go either way, so that we're being fair. So Al, Beth, and Casey, if I tell Beth and Casey to just switch positions, Casey, you go in the middle, and Beth, you go on the right, I have not formed a new and distinct 3-person group. This is still the group Al, Beth, and Casey, even if Casey and Beth have reordered themselves. In fact, BAC, BCA, CAB, CBA, these are all exactly the same group, because again, order does not matter. It doesn't matter if I switch the order of the letters in the group around, I'm still going to have the same group for any 3 given letters. However, in a permutations question, the order absolutely does matter, and the reason that order matters, the reason that when we move the letters in the group around, we form a new and distinct group. That word is actually important. That might show up on these questions. Distinct just means new, unique, different. That's all the word distinct means. So when I have positions, when I have a president position, a vice president position, and a secretary position, if I now tell Beth and Casey to switch positions, I am literally telling them to switch positions. Now Casey occupies the vice president position and Beth occupies the secretary position, in which case I have a, again, new and distinct group. I have a new and distinct student council. So in a permutations question, when you do have particular ranks or positions for each person in the group, when you move those letters around, when you change the order, it will matter. You will form a new and distinct group. Now, some students still, after I explain all this, they'll have a little bit of difficulty figuring out whether they're looking at a permutations question or a combinations question, and that's okay. It takes some practice. But I will tell you that in my experience, the easiest way to determine whether you are dealing with a permutations question or a combinations question is you read the question and you figure out whether the question is telling you whether each member in the group has a specific or named rank or position. So in the case of the permutations question above, 5b, that we just looked at, we are told that there is a specific named rank or position for each person on the student council. There is a president, there is a vice president, and there is a secretary. That is a dead giveaway that you are dealing with a permutations question and not a combinations question. So that's your visual clue. That's the clue that will tell you whether you are dealing with a permutations question or a combinations question. On the ACT, a huge number of the counting and grouping questions will tend to involve either that fundamental counting principle that we talked about on the first page or permutations, which we've just talked about here. Combinations questions are not all that common on this test, but we will go through how to solve combinations questions. In terms of the solution methods, I'm going to give you a few different solution methods. The first of them is the listing method, and as we start to go through this, students tend to start rolling their eyes and thinking, this is crazy, this takes forever, it's really tedious, I don't know why I should ever have to use this, or I don't know why I ever would have to use this, but I will tell you there have been a select few questions that have shown up on the test where the listing method actually is your best bet, where the other two methods that I'm going to teach you either will not work nicely, will not work at all, or will be very confusing to figure out how to make them work. So we do need to go through the listing method. Yes, it does take some time and energy to do the listing method, but even within the listing method, there are some shortcuts. So the key to the listing method is to lock the leftmost items for as long as possible, changing only the rightmost item until you have to change something on the left, until you have exhausted all possible groups for a given leftmost item. So for instance, in that example that I did on the first page to illustrate the fundamental counting principle, you will recall that I did A1, A2, A3, A4. Well, that's an illustration of the key to the listing method. What I was doing is I was locking into place that A letter on the left, and I was only changing the digits on the right, the 1, 2, 3, the 4, when I exhausted all the possible groupings for that A leftmost letter. I then went to my B's, did B1, B2, B3, B4, then went to my C's, so on and so forth. So instead of jumping around and doing A1, B1, C2, D3, whatever it might be, you definitely don't want to take a haphazard, unsystematic approach like that. You want to, again, keep the letter in the leftmost column locked for as long as possible, only changing it when you absolutely have to. Let's take a look at how the listing method would work on the questions that we just saw. At the top of the next page, we have, again, the questions that we were just looking at, the combinations question, the permutations question. There's no difference between these and the ones that we saw on the previous page. They're just reprinted here so that we know what the heck we're doing. So again, I'm going to name the 5 people that the 5 candidates that we're talking about here. So again, we've got Al, Beth, Casey, and now we've got Dave and Eleanor. I don't know. And there are some questions on which you are going to want to assign your own letters or numbers to the members, the candidates, the items, whatever the question is talking about. So for the combinations question on the left, here's what we're going to do. I'm going to circle that again. Obviously, the first and simplest group that we want to keep track of is ABC. Now, what I'm going to do is I'm going to lock into place the leftmost columns here, the A and the B, and I am only going to change that rightmost column. So I can do another A, B, and I can put a D in there, right? I have A, B, I did C. Now I'm doing A, B, and then D. By the way, it does sometimes help to have the letters actually written out so that your eyes can sort of see, what you're going from and to. Might make it a little bit more visual for some of you and easier to process what's going on. I still can keep A and B locked. I would then do A, B, E. Now this next step is where a lot of people go wrong. So I'm going to draw a little padlock there. I need to unlock one of those columns because I've exhausted all of my listing possibilities, all of my grouping possibilities for A, B as my starting two letters. I'm going to keep the leftmost column the same because I still have some more A's to do. I'm going to change the middle column to C. I've done my A, B's. Makes sense that I would go next alphabetically to my A, C's. Now, almost everybody either has hesitation or just flat out gets wrong what needs to go here. A lot of people will say that you need to go to A, C, B. That's not correct. The reason we don't want to go to ACB is that ABC is exactly the same as ACB. Remember, we talked about the fact that on a combinations question, for any three given letters, you can only form one group, or at least one distinct or different group. If I write ACB here, I will be double counting the ABC group because ACB is not distinct from ABC in the case of a combinations question where the people on our team, or in this case council, don't have particular ranks or statuses or positions. So I do need to go to ACD. Again, I can lock AC into place. I did ACD. I can then do ACE. So again, ACD and then ACE makes sense. There are no more ACs because there's no more letters after E that I can throw in. By the way, that little question, that little sticky point here where students won't know whether they go to ACD or ACB, you might want to write this note over here. When listing combos, okay, specifically when we're listing combos, this note will not apply to permutations, but when listing combos, the letters, if indeed you're using letters, should always be in alphabetical order. If you list a combination like ACB, where you go from A to C, so that's forward in the alphabet, but then you're going back to B. So again, you go from A to C and then you go back to B. Most likely you are double counting something. Most likely you are rewriting a group that is not distinct from a group that you have already listed. So generally when you're listing combos and you're using letters, the letters should always go in alphabetical order. If they don't, you probably screwed something up. So we did our ACs. Now we've got to do our ADs. We got A, D. The only possible letter that can go in that third column will be E. There's no letters after E, so we're done our ADs. There are no AEs to do because, again, we have no more letters over here to go forward to in alphabetical order. So we're done with our A's. Now, at this point, we've got to switch that first column. We tried all of our A's. We've now got to try our B's. So what can I do? I can do B, C, D. B, C, D, locking into place B and C. I have another B, C to do. B, C, E, B, C, E. That is all the BCs that I can do. Next, I would have a B, D, E. So B, D, E. Again, keeping that first column the same, but now I can switch my second column because I've exhausted my BCs. I've done my BDEs, B, D, E. There's no more BDs I can do because I'm out of letters. There's no BEs I can do because I'm out of letters. But I can now, I've exhausted all my B's, I can now go to C. I'll write my C here, C, D, E, C, D, E. And no more C's, no more CDs because there's no more letters, no more CEs, no DEs, no E's. So I am done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all I do. When I think I'm done, I count them up and I'm finished. So that's the listing method for the combinations. Now for permutations, again, I'm going to circle this. I've got ABC, ABD, ABE. Exactly the same as the first three combinations that I listed, but here's the big difference. Now, sorry, that's supposed to be an AC. So I locked AB into place. I exhausted all my ABs, so now I'm going to switch to ACs exactly the way that I did over here. But now, because this is a permutations question, I do need to go back and grab the ACB possibility, because remember, we've got a president, we've got a vice president, we've got a secretary. Now, president, vice president, secretary, ACB is a different student council than A, B, C. So I have ACB locking into place, the A and the C. I do ACD and then ACE. Okay, so ACD, ACE. Now I can unlock the middle column to go to my Ds. I've done my ABs, my ACs. It makes sense that I've got to go to my ADs. So again, I'm going to go AD, ADB, ADC, ADE. So ADB, ADC, ADE. And then, of course, I go to my AEs. I should do AEB, AEC, AED. Now, listen, at this point, almost everybody's thinking the same thing. One, they're thinking, this is really hard and I don't really get it, and I'm never going to be able to do this on my own or do it quickly. That quickly part is a very common thought among students. They'll be looking at this saying this is going to take forever and the ACT is very fast paced and I'll never have time to do all this. What I will say to that is, one, with some practice, the listing method, you saw me do it fairly quickly. The listing method does get faster and faster and faster. You just start to get into a rhythm. You start to learn how to write these groupings faster and faster and with more confidence. The other thing is that even with permutations, so at this point students are looking at this going, we've just finished our A's and now we've got to do our B's and our C's and our D's and our E's. This is ridiculous. But with the listing method, you can almost always extrapolate. You can almost always look at what you've done up until a certain point and say, okay, well, for my A's, there are 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that's 3 times 4, right? 1, 2, 3 times 1, 2, 3, 4 columns, 3 rows, 4 columns. So there are 12, that bracket is ugly. Let me get rid of that. There are 12, much nicer. There are 12 possibilities for our A's. So what I'm going to do down here is I'm going to write, okay, 12 A's. Well, that means that for B as the starting letter, we will have 12. For C, we will have 12. For D, we will have 12. For E, we will have 12. In other words, once we find out that there are 12 possibilities when we're starting with A, we know that there's going to be 12 times 5 total, because there are 5 total starting letters if we just multiply the number of groupings that we have starting with A by the number of possible starting letters that we can have total. We will get our total number of permutations. There will be 60 possible permutations, 60 possible student councils that can be formed here. So again, if you feel overwhelmed by the listing method, you are not alone. If you're worried about timing, if you're worried about ease, not at all uncommon, which is why in the homework, when you are doing counting and grouping practice questions, it is a good idea, even if you do a certain question in a different way with a different technique, you might want to also try the listing method just so that you can get some practice with it, so that you can see how the listing method would work. Again, the listing method is not all that commonly needed, but there have been a few questions on which the listing method was by far the safest, easiest, possibly even quickest way to go. The box method. The box method we are only going to be using on permutations, and since you have already seen the box method before, we did this on the first page when we talked about the fundamental counting principle, this should go fairly quickly. So what we are going to do for the box method on permutations is we're going to draw a horizontal, I'm going to highlight some of this, draw a horizontal set of boxes. We got to draw one box for each of the positions or ranks that needs to be filled. We are going to fill in each box with the number of options that we have available for each position, and then we're going to multiply those numbers together. In other words, we're going to apply the fundamental counting principle. So number 6, once again, we have this student council question. We're not going to read through it again. You can try the box method on number 6 if you'd like. Pause the video. I'm going to go ahead and do it right now. Again, I'm not going to read this question again because we've seen it 3 frickin' times already. So we're being asked how many different student councils are possible. So what we would do here is we have 3 positions. So I'm going to, as step 1 up here says to do, I'm going to draw 3 boxes. That's the president position, the vice president position, and the secretary position. I am in the first box going to fill in 5 because there are 5 candidates running. But this is one of those single pool questions that we talked about a couple pages ago, where we have to understand that as soon as we pick our president, there will only be 4 options left for vice president because we've already filled the president position. Now that we filled the vice president position, there are 2 people that we have to take out of our pool, out of our group. We have a vice president and a president, which means there's only 3 people left to run for or serve as secretary. And again, according to the fundamental accounting principle, if there are 5 ways to pick a president, 4 ways to pick a vice president, and 3 ways to pick a secretary, I will have 5 times 4 times 3. I should be doing this in the calculator. So 5 times 4 times 3. Again, I know some of you can do that in your head. I can do that in my head. It's safer to use the calculator. We are allowed to use the calculator. We might as well take advantage of it. So there will be, as we found in the listing method, 60 possible student councils on this particular question. Box method on permutations, example 7. In example 7, I would suggest going ahead and doing example 7 on your own. If you are feeling confident. If you are not, you can watch me work through it right now. How many different 3-digit positive integers can be formed using the digits 2, blah, 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 if the units or ones digit is 2 and no digit is repeated within each integer? So what I'm going to do here is I am going to draw 3 boxes. Why am I drawing 3 boxes? Because it's a 3-digit positive integer, which means I have a hundreds digit, I have a tens digit, and I have a ones digit. Now, very, very important in this question, I'm going to go to this phrase here. I'm going to highlight this. You don't have to highlight it. I'm just making this stand out. They tell us that the units digit, or the ones digit, that's this box over here, is 2. Now, a lot of students make the mistake of taking this 2 and plugging that 2 into the ones digit position. But remember, in these boxes, we are not putting the actual number that we're choosing in that position. We're not putting this 2 because we're choosing a 2. We're putting the number of options that we have available to us. Because the units digit has to be 2, we have only 1 option. This is the number we're choosing. This is the number of options that we have. So there should be a 1 in that box. Once we choose the 2 for the ones digit, the 2 is no longer allowed because no digit can be repeated, which means we have 1, 2, 3, 4, 5, 6 options for the hundreds digit. As soon as we pick the hundreds digit, we will then have only 5 options left for the tens digit. So fundamental counting principle, box method for permutations, they both say that we now multiply these numbers in the boxes together, and of course we're going to get 30 here. That is the box method on permutations. There is a variation of the box method for combinations, but it is almost non-existent, a question where you would have to use the box method for combinations. So we are not going to go over the box method for combinations right now. At the top of the next page, we finally get to, I guess you would call this the payoff, because there is a very simple calculator method that you can use on very straightforward combinations or permutations question. That student council question that we've been looking at for the last few pages is a good example of one that is a very straightforward combination or permutation question. On questions like the student council question, your calculator will have some built-in functions that will allow you to perform the calculations that we did using the listing method, using the box method. You can perform these calculations in a matter of seconds with the calculator methods. I want to be clear here, when I say calculator method, you can use the calculator on the box method that we did on the previous page. That's perfectly fine. What we're talking about here is really a pure calculator method where the calculator actually has a function that will allow us to make these calculations. Those functions are the NCR and NPR functions. So first of all, I will tell you what those are in a moment. I know that they can look a little bit weird and strange for students who haven't seen them before. Let me just tell you where they are on the TI-84. You can get these functions are also on the TI-Nspire and pretty much every graphing calculator. The TI-Nspire, the TI-84, all you have to do is go to, there's actually 2 ways. On the newer TI-84 Plus, there's another location in which you can find these, but for general TI-84 users, whether it be the CE or the older TI-84 Plus or TI-84 Plus Silver Edition, what you're going to do, I'm going to do that one more time. We're going to go to Math, then we are going to go to Probability, and then you can see numbers 2 and 3. There's number 3 NCR, number 2 NPR. That's where we locate these functions. So again, that is the Math menu. You've got to arrow over till you get to the Probability column, and then you find NPR and NCR in numbers 2 and 3. Again, on the newer, I'm going to quit out of here, quit. On the newer TI-84 Plus CE, and actually on some of the newer just regular old TI-84 Pluses, you may be able to access these using the alpha and then window button, which brings up that F2 menu. So again, I've hit alpha, I'm now hitting the window button, and I can see that numbers 7 and 8 are my NPR and NCR functions. So on the TI-84 Plus CE, I generally do use the alpha window sequence. It's just a little bit easier, a little bit more efficient to get to. Now, what the heck are these things? So all of this stuff is explained down here, so you don't really need to write any of this down. But when we see NCR, when we see NPR, the N is the total number of things that we have to choose from. So in the case of our student council question, in each case we had 5 total candidates to choose from. The R is the number that we will actually choose, the number that we will actually select. So we were selecting in each case 3 people to serve on the student council, and then obviously the difference between the C and the P is that C stands for combinations and P stands for permutation. So in order to use the calculator method, you are obviously going to need to determine beforehand, before you do any of these calculations, whether you're dealing with a combinations question or permutations question. And that goes back a couple pages ago where I told you that you can almost always recognize a permutations question because the members or items in the group will have a particular rank or status or position. So let's go one more time to these darn student council questions, and let's see how this would work. This should go very quickly. We have, for the combinations question, again, 5 total candidates. That comes from there. We have 3 members, 3 people that we're going to choose from those 5. So what we do is we go into our calculator. You know what? I'm going to do this using the old TI-84 because there is a little funky thing here that you should be aware of. Let me get out of that graphing screen real quick. The funky thing that you need to be aware of is this. In the old TI-84 Plus or TI-84 Plus Silver Edition, what your calculator is going to do, if you go to Math and then PRB and then NCR number 3, you're going to see that the calculator is inserting this answer. And what the calculator is doing is it is inserting whatever the most recent calculation, the most recent result that you got. The calculator is inserting that result here. So in order to clean that up, you either can just go over the A and answer and hit 5. If you do need to enter 2 digits here, you got to be very careful, because as soon as I hit the next digit, we're going to overwrite the NCR, which brings me to my next point, which is this, that if you don't want the calculator to do that screwy thing where it inserts this number, just hit the 5 first, then go Math, PRB, NCR. I'm going to hit number 3 here, and now the calculator won't insert the result from the previous step. So I'm going to hit 3 and then enter, and indeed, remember that was the number of combinations that we got when we were doing the listing method. I should have circled this. Now with NPR, I'm going to do NPR with the newer calculator. So I am going to do this with the newer calculator, am I not? Yes, I am. There we go. Now, the newer calculator actually makes this a little bit nicer, a little bit neater, because when we go into Math, PRB, or probability, and then number 3, again, we could have accessed that using the alpha window sequence, but now we have these little boxes for our subscripts here, so we can hit 5 and 3 and enter, and again, I get 10, same thing I got here. Now for, I said I was going to do permutations. I guess I was just confirming combinations. Let's do permutations. So for permutations, I'm going to go Math, probability, NPR, and I'm going to write this down first, 5, permutations, have to choose 3 at a time. So 5, P, and then the 3, and indeed when I hit enter, I get 60, which is what we got both in the listing method and in the box method. So again, you know, if you're on a straightforward combinations or permutations question, there really is no doubt that the NCR NPR method is going to be easiest. Of course, if you are going to go this route, well, really, if you go any route, you've got to know whether you're dealing with a combinations question or a permutations question before you start. On example 8, at the bottom of this page, I would suggest trying this question on your own before watching me go through it, especially if you are feeling confident about all this stuff. We've got a coach must select a starting squad of 5 players from the 13 players on the team. How many different starting squads can the coach select? So first things first, let's circle what they're asking. How many different starting squads? We have to determine whether we're dealing, if we want to use the calculator method, we have to determine whether we're dealing with a combinations question or a permutations question. And of course here, you should take a stab at what we're dealing with if you haven't already. We are dealing with a combinations question. And the reason that we're dealing with a combinations question is because the starting squad, there's no positions on that starting squad. If we had, you know, a forward and a back or something like that, then okay, we'd have a permutations question. But here we're just choosing 5 players, which means that, you know, A, B, C, D, E, that starting squad is absolutely no different from A, B, C, E, D. These are the same starting squad. In other words, order doesn't matter. There's no rank or position for each of these players, which means, again, we're dealing with combinations, which means this is going to be as simple as doing 13, choose 5. 13 is the total from there. 5 is the number we're choosing from there. So we are just going to go in our calculator. In fact, I'm going to do a little copy paste here so I don't have to go back into the menu. And I'm going to do 13 down there on the left, 5 down there on the right, and I'm going to get 1287. Although, as I've said before, there is also a possibility that ACT would simply leave the answer as 13C5. Other answers might be, you know, 5C13 or 13P5, but this would be the right expression if indeed ACT left the answers as C or P NCR NPR expressions. At the top of the next page, finally, we get to the final portion of this discussion. We get to repeated elements. Repeated elements could also just be called identical items or identical elements. What we're talking about here are situations in which we are going to permute a certain number of letters or numbers, but the group of letters or numbers that we're permuting have identical elements. In this case, it's these two S's. So if you look at these two questions, they're both asking number of distinct permutations of the letters in a certain word, and these are both 4-letter words. We have tops on the left, sops on the right. Some students might look at these two questions and think they are identical to each other. There's no difference between these two questions because there's 4 letters, and if you're permuting 4 items, you're going to get the same number of permutations. However, no matter what those items are. However, it is true that in the case of tops on the left, we're going to get 24 distinct permutations. But over here on the right, what you will notice, if you really look at this with an eagle eye, is that by the time you get into this second column here, you are starting to repeat listings that you already have. OPSS is already listed here, OSSP was already listed here, and OSPS was already listed all the way up here. So the bottom 3 permutations here, they are not distinct. They are groups. They are not new or different groups. And remember, that's what the word distinct means. And that's why I said before, it's very important that you understand what that word means. Same thing in the third column, we get POSS. That was already here. PSSO, PSOS. And in the last column, every single one of these 6 groupings is the same as a grouping that we have in the first column. We have SSOP there, we have SSPO there, we have SOSP there, SOPS there, SPSO is there, and of course SPOS is there. Now, why is this happening? Well, of course, it's because of those identical elements, those 2 S's. What that means is when I have, let's say, OPSS and then another OPSS, if the 2 S's were, let's say, different colors, let's say one was blue and the other was red, okay, fine, maybe these would be distinct permutations because in one case the blue S is the third letter and in the other case the blue S is the last letter, but these two S's are not different. They are indistinct, they are identical, they are repeated elements, in which case OPSS and OPSS become identical groupings, which means the second one is not, again, distinct. So what ends up happening here is we end up cutting in half. We end up cutting in half. We've got 6 there, 3 there, 3 there. That makes 12. The number of permutations that we had in tops when we get to the SOPs word, again, we have only half left. Now, how do we actually deal with this practically? What formula can we use? What system can we use? There is a formula, fortunately. Again, this is one of those cases where the formula will be a little bit confusing to understand until we actually look at this with some numbers and maybe the example we just did. We do need to know for this formula what that factorial symbol means, that exclamation point. You can see the exclamation points here and here. The factorial symbol, some of you already know this, but all the factorial symbol means is that you take the number that is to the left of the exclamation point and you scream that number at the top of your lungs. That's what the exclamation point means. I'm just kidding. That's not true. Don't do that, and definitely don't do that in the middle of the test because you'll get kicked out. What we do is we take the number that is to the left of the exclamation point and we multiply that number by all of the integers less than that number all the way down to 1. So 3 factorial means 3 times 2 times 1. 4 factorial would mean 4 times 3 times 2 times 1. 5 factorial, and so on and so forth. The factorial function in your calculator is in the same exact place that NPR and NCR are located. We have math, we have prob, and then you can see number 4 is your factorial symbol. So if I were to type in, I'm going to do number 4 right now. Let me go put in 3 factorial, and of course 3 factorial is 6 because again that's 3 times 2 times 1. Now you on the CE calculator you can also access your factorial function in the alpha window F2 menu, that F2 menu. We have the factorial symbol there as number 9. Again, a little bit easier to access there. So here's what we do for repeated elements. We, in the numerator of a fraction, put the total number of permutations that we would normally have without any repeated elements. So in the case of tops, we can see that we would have 4 factorial total permutations. Now why is that? Well, think about the box method. The box method looks like this. We have 4 letters for our first letter. Then once we choose that letter, there's 3 letters left for the second letter, and then 2, and then 1. Well, 4 times 3 times 2 times 1 is just 4 factorial. That's where that 4 factorial comes from. Then in the denominator, what we need to do is we need to divide by, in the denominator, the factorial of the number of repeated elements. So in the case of SOPs, we have 2 repeated elements, so we are just dividing by 2 factorial, and that is how we get down to 12. Now, a question or two have shown up on the ACT that had multiple repeated elements, so we are going to look at number 57 at the bottom, but we'll do a fun one first. Let's look at Mississippi. If you want to try it on your own, you can. What I want to know is what is the total number of distinct permutations of the letters in the word Mississippi. So like I said, if you want to try it on your own, go ahead and try it. I'm going to work through it right now. There's 11 letters in Mississippi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the total number of permutations without any repeated elements would be 11 factorial. 11 times 10 times 9 times blah, blah, blah. Now what we have to do is we have to start dividing by the factorials of the repeated elements, but we need to consider each type of repeated element, in this case the I's, the S's, the P's, as separate, and we need to divide by a separate factorial for each of those types of repeated elements. What I mean by that is this. There are 4 S's, 1, 2, 3, 4. So I need to do 4 factorial, that's for the S's. Then there are 4 I's, 1, 2, 3, 4. 4 factorial, that's for the I's. And then there are 2 P's, 1 P, 2 P's. So 2 factorial, that's for the P's. So again, we are separating into 3 separate factorials each type of repeated element. We have the S type, the I type, and the P type. That's what we need to do if we have multiple types of repeated elements. I'm not going to go ahead and figure out what this is. It's really not important that you calculate this, just that you're able to set it up. I would go ahead, now that we've done a couple of examples, to try 57 on your own. Pause the video, try it on your own. We need distinct permutations of the letters in sleepers. So again, remember it's formulaic here. We've got 1, 2, 3, 4, 5, 6, 7, 8. 8 factorial would be our regular old normal number of permutations here. And then in the denominator, what do we have? We have 2 s's, so we need a 2 factorial. And then we have 1, 2, 3 e's, so we need a 3 factorial. Now again, before we go in the calculator and calculate this all out, we should take quick look at the answers and see that the answers are actually in factorial form. They are not calculated out, which means we can just pick the answer that looks like what we have here, which is answer choice E. Final note, really important that you don't make the mistake of thinking that 2 factorial times 3 factorial equals 6 factorial. That is not true. You cannot simply multiply the 2 numbers to the left of the exclamation points and then put a new exclamation point after the product of those 2 numbers. 6 factorial is actually much, much, much bigger than 2 factorial times 3 factorial. That is it for counting and grouping. Again, there is quite a bit to know here, but most of this stuff, as I just mentioned a moment ago, is pretty formulaic. You've got to know the fundamental counting principle. You got to know the difference between combinations and permutations. You got to know the 3 solution methods. Yes, if you get lucky, a lot of the questions that you see will be the NPR, NCR method, or maybe even the box method. Hopefully you won't see too many listing method questions, but if you practice the listing method, it shouldn't be too burdensome for you. And then finally, you need to know how to handle repeated elements on the off chance that you get a repeated elements question.